Hello everyone. Today I'll be presenting our paper Path to Circuit Characterization of Stealthy Crosstalk Attack on Multi-Tenant Superconducting Quantum Hardware, which has been accepted to the ACM QSec 2025. I am Sohiti Matuddin Shubho, a first year graduate student, and this work has been advised by my supervisor Dr. Tasnuma Farhin from Louisiana State University. I will start by discussing the motivation, key research questions, and existing literature. Then I will detail our threat model and attack framework. The core of the talk will be in the analysis and results, where we will explore the impact on different quantum protocols and then characterize the attack itself. Finally, I will discuss the implication of our findings, propose a mitigation strategy, and conclude. In the near future, multiple users will often share the same quantum processor, a model known as the multi-tenant quantum computing. Now, as you can see here, different users are assigned disjoint sets of qubits, but these qubits are still physically coupled. Now, crosstalk can be classical from the control line leakage or quantum arising from the inherent Hamiltonian coupling between the qubits. In this work, we focus on the quantum crosstalk as it provides a vector for sophisticated pulse level attack. Now, this leads us to three core research questions. First, can we systematically exploit crosstalk to actively compromise computational integrity? Second, do the adversarial qubits play a distinct asymmetric role in the attacks? And third, how robust and stealthy are these attacks against the typical hardware variations like frequency detuning? Now, traditionally, crosstalk has been treated as noise or fidelity issue that needs to be calibrated away. More recent security research has viewed it as a passive side channel for information leakage or victim pulse definition modification. Our work addresses a critical gap. We investigated crosstalk as an active injection vector for integrity attacks, and we provided the first end-to-end framework to map these physical pulses to logical error models. Now, our threat model involves an attacker Eve and a victim Adam on a shared quantum processor. Eve has full pulse level control over her qubits Q0 and Q1. Adam, the victim, operates his qubit Q2 using standard gate commands, completely unaware of Eve's activity. Crucially, Eve has no direct access to Adam's qubit or his circuit. Her objective is to manipulate Adam's computation by exploiting the physical crosstalk between their qubits. Now, to model this, we use a time-dependent Hamiltonian in the rotating frame. The Hamiltonian has two parts: a static term for the inherent hardware coupling and a time-dependent drive term representing the adversary's microwave pulses. Now, we simulate the system's simultaneous evolution using Q2's master equation solver, focusing on the coherent effects of the attack without the environmental noise. Now, the adversary Eve has two main strategies based on the timing. She can inject her pulses before Adam's operation or after, which we call the attacker first and the victim first respectively. And she can also control various pulse parameters, such as the amplitude. So for Q0, Q1, it's A0 and A1. And the frequency detuning, which is the difference between the drive frequency and the resonant frequency, the shape, such as the cosine, chip, or rate pulses, which is listed here. Now, our first step was to identify which crosstalk channels are most dangerous. So, we fixed a reference pulse in the Q1 and varied drive of the Q0, measuring the deviation in the victim's output Q2 in the probabilities, and we found that the off-diagonal couplings such as the YX and ZX combined with the cosine or the chirp pulses, these are the most damaging ones. Now, it also revealed a profound vulnerability. An attacker on the Q0 can affect a victim's circuit in the Q2 by the intermediate qubit Q1 as a conduit. We call this attack through neighbor. Now, we will look at the impact of these attacks on three different quantum protocols. In our setup, the attack can be injected at point A or the point B, which is the attacker first and the victim first, relative to victim's code operation, which we will call U, and this is the U for the coin flip and the XOR classifier. Now, First, a simple state preparation task, which is a biased coin flip. And here, the ideal probability of measuring one follows the sine square curve, which is in the red. And as you can see, the attacker first strategy in orange causes a massive predictable deviation from the ideal outcome. The victim first strategy is more subtle, and at certain angles become nearly undetectable, highlighting the potential for stealth. Now, in the stark contrast, the XOR classifier is remarkably resilient. As the graph shows, even under the maximum attack amplitudes, the deviation in the output is minimal. This hints that the vulnerability is not universal but highly protocol dependent. Now, our third case study, a single qubit quantum neural network reveals a catastrophic vulnerability. The model is trained for binary classification on the ID's dataset and a single-step training process, creating polynomial features, then solving a linear least square problems to determine the coefficient, which are then used to map each data point to a y rotation angle in the quantum circuit. Now, while the victim first attack was harmless, the attacker first strategy completely destroyed the model's performance. As the hitman shows, the classification accuracy becomes equivalent to random guessing. So, to summarize these three cases, the coin flip and the single qubit quantum neural network, which rely on the precise initial states and continuous rotations, are extremely vulnerable to attacker first strategy. The XOR classifier, which has discrete operation, is highly robust. So the key takeaway here is the vulnerability is algorithm dependent. So now, moving from the impact to characterization to understand what the attack is doing at a logical level, we developed a framework to map the physical pulses to an interpretable circuit. And here is the circuit. And we model the effective error on the victim's qubit as a single parameter y rotation, the ry theta. And why we used only the ry theta? Because it is the single parameter, so we can easily track it, and also it's a real valued rotation, and it simplifies the model, and we can easily interpret this. And also we note that if there is no pulses in the q0 and q1, when they're 0, the gates in the q2 cancels out, so this becomes a identity. So this actually checks out. And when this is not, it will create a active attack vector, and it will be clear as a signature. Now, from okay, so we also note that we can actually derive the Krauss operator from this circuit, because this represents a quantum channel. And now we also now we want to match this circuits quantum the same quantum channel, which actually comes from the pulse level attack, right? So now to do this, we want to do the circuit fitting via the isometry optimization. So the first step is we use the quantum process tomography to experimentally reconstruct a complete model independent description of the error channel induced by the attack. From this, we can extract its Krauss operator, the K experimental. So the experiment, how we can do this? We actually need to calculate the Choi matrix first, and then we can just take the eigen decomposition. And of course, there is our logical circuit, and we can extract the Krauss operator as well. Now, here we perform a joint optimization over the logical rotation angle theta and unitary isometry u to find the best fit between our simple circuit model and the complex experimental channel. And you can see this actually comes from the isometry Gauss freedom, and we actually this is a mathematical fact, but we basically use this here to find the value of theta, and which actually provides a quite few insights, which we will see in the next slide. Now, here, this characterization yields a very powerful insight that robustness against the frequency detuning. And we can see that from the plot, the variance is in the order of 10 to the power minus 6, which is a critical security result. It means an adversary can launch a predictable attack without needing perfect real-time knowledge of the hardware's calibration. So this is actually very powerful and critical. Another insight, I will actually discuss two things at once. So first insight is the asymmetric driver versus catalyst. So our analysis revealed that the two adversarial qubits, the Q0 and Q1, they play fundamentally different roles. As we can see from the top plot, the amplitude of the Q1, it directly controls the strength of the induced rotation, but the Q0, it barely changes the rotation angle. Now, in the bottom plot, we can see that the increasing the amplitude of the qubit Q0, the catalyst, it does not change the theta, but it reduces the fit loss, meaning it makes the attack more coherent and better match for our ideal logical model. This shows a sophisticated true prolonged attack mechanism. And we also see that the pulse shape, the choice of the pulse shape, it actually allows the adversary to make a strategic trade-off. The cosine and chirp pulses are very aggressive, inducing the largest error, but the square and drag pulses are more coherent and targeted, resulting in a stealthier attack than that better aligns with a simple logical error. Now, is the same thing I just discussed here. Now, what are the broader implications? First, the quantum crosstalk is not just a random noise. It's a structured attack vector. Second, the attack can be incredibly stealthy and also highly dependent on the interaction between the hardware and the specific algorithm being run. So finally, the existence of driver catalyst role and the non-local attack pathways means security must be considered at the physical device topology level. Okay, so what are the mitigation strategy and the future works? Now, based on our finding, we propose a two-tiered mitigation strategy. For the detection, the system can run simple sensitive canary circuits such as the coin flip to monitor the anomalies. And upon the detection of an attacker first signature, the system can perform a high fidelity state reset for the containment, which nullifies the primary threat and forces the subsequent attack into the much less damaging victim first regime. Now, the future work will focus on adding more noise model, validating on hardware, extending the study for more topology and multi-qubit protocols. Also, how to use it for side channel attack. I mean, it can provide a analytical description of that as well. So this is so thanks for your attention. I will be happy to answer any questions. You can also reach out to me via my emails. So thank you very much, and